So today I really have the honor to introduce Josh Lepawsky. I've known Josh for a couple of years now, I mean decades maybe. Josh is a professor in the Department of Geography at Memorial University in Newfoundland, Canada, the east coast of Canada. And he's done his Bachelor of Arts in Geography at UBC in Vancouver, and then a Master's in Geography as well in Queen's University, and a PhD in Geography at the University of Kentucky. Josh is the director of the Electronic Planet Research Lab, where he and his group research the relations of people, places, and things that enable the existence and continuation of digital technologies. So his research is generally directed towards geographical, empirical, and conceptual alternatives. So he brings a really all rounded up perspective to those key questions related to electronic and electric waste. So two areas of particular interest of his EPR lab are the so-called discardscapes and repairscapes. And I think we will be hearing a little more about this in today's lecture as well. Just a side note, when Josh speaks of discardscapes, and when I learned about his concept, it really was like an insight of a more fully understanding of the pathways of discard and the impacts they generate. So when he speaks of discardscapes, he refers to the impacts generated along the progression from extraction to consumption, often leaving behind toxic trails. And this is something which usually is not unveiled. And I think with his research, it has become very clear in the context of electronic waste, but it can be applied to all other kinds of wastes we are generating. So I'm really happy and looking forward to your keynote speech today, about scale, magnitude, indeterminacy, and some ways they matter for acting on the bin. So the word is, I hand it over to you, Josh.
All right. Thank you so much, Jutta, and thank you, Allison, and to everyone who has organized Opening the Bin 3. It is a real pleasure to be here remotely, and it is a genuine honor to have been asked to deliver this keynote. So I'm just going to take a moment to share my screen, and I'm just going to check that everyone is seeing that. I don't know if Jutta, you're able to indicate that you can see it. Okay, perfect. Okay, perfect. So as Jutta mentioned, my title today, Scale, Magnitude, Indeterminacy, and Some Ways They Matter for Acting on the Bin. I'm really looking forward to delivering the talk and then hopefully questions and discussions that will emerge after it. And in the next few minutes, I'm going to make three linked claims. The first is that it's important to carefully conceptualize terms that are sometimes used interchangeably, namely waste, dirt, and discard. Second, I'm going to claim that it is important to distinguish between scale and magnitude. And that claim I'm going to examine through some examples related to pollution from mining for manufacturing of electronics in relation to post-consumer electronics recycling. And then the third claim that I'm going to make is that thinking with waste, dirt, and discard clarifies a need to think and act in relation to indeterminacy rather than uncertainty. And I'll talk about what that means as I get into things. I'll illustrate that third claim through a discussion of both the temporal and the spatial magnitudes of pollution arising from electronics manufacturing at locations in and beyond Silicon Valley. So on to my first claim. As Max Liboiron has shown, assuming that there's an equivalency between dirt and waste is a mistake. It's important to remember that in Mary Douglas's famous work on dirt, that waste and dirt are not synonymous. Things that are typically thought of as garbage or trash, let's say bits of plastic, used tissues, errant rubber bands, all of those things have a rightful place, as Mary Douglas would say. They belong in a bin of some kind or another. Things like these examples of trash or garbage might be displaced or misplaced when they're not in the bin, but they are not out of place in the sense of not having somewhere to fit in a broader system of ordering. Dirt is different. Dirt is that which fundamentally does not have a place, and as such challenges the ordering of a system of one kind or another. In that sense, dirt is danger. It is an existential threat. So if dirt is left unaddressed, then the ordering of a given system is challenged with the risk of breakdown and dissipation by that which is dirt. Dirt must be dealt with one way or another to reassert order. Reasserting order is a power struggle, and struggles pertaining to power are politics. Discarding the people, places, and things that actually or potentially threaten the ordering of a given system is a technique of power. For a system to subsist and to persist, it must discard that which threatens its ordering. Unlike dirt, waste can be sorted, for example, into bins and then into landfills. Waste might be litter, for example, when and where plastic bags clog a ditch or are caught in trees, but litter doesn't automatically challenge the systems that make fossil fuels into plastics and plastics into bags. Dirt, on the other hand, must be eliminated. It might help to think of CO2 as something that is shifting from being waste, for example, in the sense of emissions, to becoming dirt. That is something that is challenging the subsistence of more and more interlocking systems. So to my next claim, and that is that there is a tendency to use the idea of scale as a synonym for differences of size. In my research on pollution and waste arising from the lives of electronics, I've found it useful to think differently and to distinguish scale from magnitude. It's helpful to think of scale as relationships that matter, where differences in size, whether absolute or relative, might be of secondary importance or may not matter at all. So for example, if you returned home one day to discover that you'd accidentally left the bathtub running, causing it to overflow, you could try to quickly run around with a mop to soak up the excess water. But of course, a better response would be to turn off the tap before mopping up. Now, all of those teeny tiny H2O molecules flowing around the room didn't automatically add up to a big flood without, among other things, the running tap, the tub, the stopper, and your forgetfulness. The scale of the situation is about the relationships that matter rather than being inherently about relative or absolute size. So if scale is about the relationships that matter, magnitude is about the extent of something. The importance of the distinction becomes evident when thinking about waste. We'll come back to this yellow circle in just a minute or two, but first, let me take you on a bit of an empirical journey into pollutants released from the electronics manufacturing sector in the NAFTA region, Canada, the US, and Mexico. Okay, so this is a version of a map I made for a recent publication about pollutant releases from electronics manufacturing in Canada, US, Mexico. And the map does a few different things. First, it shows that between the years 2006 and 2017, which were the most recent years of data I had available to me at the time, facilities involved in manufacturing electronics in these three countries released 366 million kilograms of 104 distinct chemical pollutants. And on the right-hand side of the screen where the legend is, you see, I'm sure it's far too tiny to read, but that list of 104 different chemical toxicants, and they've each been assigned a color. The map also shows that pollutant releases from the manufacturing of electronics happens ubiquitously but unevenly throughout this region. It's certainly well beyond one of the places that we might most associate with tech, that is Silicon Valley, which you see pointed to on the left-hand side of the map. But the map also violates some cartographic conventions deliberately. And one of those cartographic conventions is the idea that a map should only use about 5 or so shades of color to make distinctions between categories because of the way human visual perception operates. And the map deliberately violates that convention because there are so many different chemicals released by this particular industrial sector, there are not enough colors to cover them all. These are also categorical distinctions. These are different types of chemicals. So it would make no sense to map these as a range of color, a continuum from one shade of color to another. These are categorical differences. So that overwhelming of even the ability to perceive sort of differences between chemical types visually is part of the message that I want to convey both in that publication but also in this talk, in terms of why it can matter to think about differences between scale and magnitude. So let me dig a little bit further into what I mean. So hold that map in your mind. We are going to come back to it in a moment. So what you see here is essentially a sort of a Venn diagram where the sizes of the circles represent the number of chemicals that each jurisdiction listed there requires companies that have facilities in those jurisdictions to disclose that they release from their facilities. So the US, for example, requires that 695 chemicals be disclosed. CEC refers to the Commission for Environmental Cooperation. That's a NAFTA body. It requires 659 chemicals be disclosed. Mexico, you can see 398, Canada, 324. And then over on the far right of the diagram, you see the EU only requires 91 chemicals to be disclosed from facilities within its jurisdiction. To add to the complication, when you look at all of those jurisdictions and figure out how many of those, all of those different chemicals are common to all of the disclosure requirements, only 10 chemicals are commonly required to be disclosed across all of those jurisdictions. Why does that matter? Well, if you think one way it matters, if you think about a globally distributed industry like the electronics manufacturing sector, even a single company, let's say Apple, is going to have facilities or suppliers in many, possibly even all of these jurisdictions. And yet from a chemical pollutant release perspective, because of these different reporting requirements, those facilities of even the same company are going to at least potentially look radically different from a chemical toxicant release perspective based on these reporting requirements. So now let's bring that set of ideas or that set of empirics back to this question of magnitude. Now, I told you to keep that yellow dot in mind a few moments ago. What you probably didn't see when I first showed you that slide is that little blue dot beside the large yellow sphere. In fact, the blue dot is probably so small relative to the yellow circle, you can't see it unless I point it out with that blue line you see or arrow that you see to the right of the yellow circle. That dot was there in the original slide. It was just too small to see. Now, that big yellow circle represents all of the chemicals tested and found toxic by the CAS, the Chemical Abstracting Service. And as of August 2019, most recently available data, there were 191,400 different records of chemicals tested and found to be toxic. That little blue dot represents what you saw a moment ago, those the number of chemicals required to be released in each of those jurisdictions. And the circles in this current slide, the yellow and the blue, are sized proportionately to the numbers they represent. So what does that mean? Well, even where regulations exist to disclose releases of chemical toxicants, the number of toxicants required to be disclosed, the little blue dot, is minuscule relative to the number of chemicals tested and known to be toxic. So this is an example of how differences of magnitude matter. So one of the things I've been interested in is, it can be easy to write these numbers down. It can be somewhat easy to visualize them, although the size of that blue dot makes the visualizing of them, if not useless, close to it, because the blue dot becomes so small. So one of the ways I've suggested thinking about this is that if chemicals were kilometers, then the number of chemicals tested and found toxic, the yellow circle, would stretch from Earth halfway to the moon. But let's carry on with that kind of comparison of magnitude. This time, between the number of chemicals tested and found toxic compared to all of the chemicals currently available for industrial use. So the big red circle is what is available for industrial use. And the tiny yellow dot that you can probably just barely make a tip of that blue arrow is what has been tested and found toxic. So if those 204 million chemicals available for industrial use were kilometers, they would stretch from the Earth to slightly past the sun. Meanwhile, the number of chemicals we know are toxic because they've been tested, the now little yellow dot, those are merely within the limits of flights by astronauts. These differences of magnitude matter. Whoops. let me just make sure, sorry. There we go, sorry. So the database from which I derived the data depicted in the map that you can see it at the top right-hand corner there, the one I introduced to you a moment ago, showed you the release of 104 chemicals known to be released by the electronics sector out of a total of roughly 700 chemicals that are mandated to be disclosed by industries in the NAFTA region. Yet, 700 chemicals amount to less than 0.4% of the 191,400 chemicals tested and known to be toxic, yellow dot at the end of the blue arrow, and less than 0.0004% of the 204 million chemicals available for industrial use. So the number of chemicals available for industrial uses exceed all toxicological testing capacity on Earth, and it is extremely unlikely that capacity could ever be sufficiently increased to have anything like full knowledge about the toxicological risks of all chemicals currently available for industrial use. So what does that mean? I would argue that to think of these differences of magnitude as gaps in the toxicological knowledge base is misguided. A knowledge gap implies a break between two objects or a space or an interval in an otherwise continuous phenomenon. Knowledge gaps imply uncertainty. In other words, we know about X and X implies Y. And while we're not sure about Y yet, we probably will be at some point. That's uncertainty. But when it comes to chemicals and their toxicology, the implications of magnitude here point to the differences between uncertainty and indeterminacy. Uncertainty describes a situation of knowledge within knowable boundaries. Under conditions of uncertainty, we may not know what particular state a system is in, but we can know that particulars cannot, say, drop below X or go above Y. Indeterminacy is fundamentally different. It is fundamentally open and unfixed. Even if it's possible to measure X and Y, it is impossible to know how X and Y may or may not relate to system behavior. Chemical geographies of pollution and waste released from electronics manufacturing makes the distinction between uncertainty and indeterminacy quite important. Let's look at some other examples of how indeterminacy and uncertainty relate to one another, this time from within Silicon Valley itself, which you see again over on the left-hand side of the map. I'm going to zoom in there for the next couple of slides. And we're going to examine the implications of the contamination of Silicon Valley landscapes by trichloroethylene, or TCE, which is a chemical toxicant known to be carcinogenic and is used in the manufacturing of electronics, both in the past and in the present, as well as other industrial manufacturing applications as well. But it is an important one in the electronics sector. So beginning in the 1970s, people living and working in Silicon Valley began to notice what would later be recognized as TCE's harmful effects on the valley's ecosystems. Up until the creation of the US Environmental Protection Agency and the passage of relevant legislation, manufacturing facilities in the valley routinely discarded chemical mixtures from manufacturing, including TCE, into those facilities' drainage pipes. Those pipes led out of those facilities and into the public infrastructure of sewers and other wastewater systems. Those chemical mixtures were typically acidic and, as a consequence, ate through the pipes, eventually leading to significant underground plumes of TCE and other chemical toxicants. By 1989, areas around 3 major electronics manufacturing facilities, those of Fairchild Semiconductors, Intel, and Raytheon, were declared Superfund sites by the EPA. I can talk about what Superfund means if there are questions about that. Magnitude and indeterminacy surround the situation here in Silicon Valley in at least 2 important ways: temporally and in terms of toxicological harm to people. Since the EPA declared the Superfund site in the valley in 1989, the EPA and various other governmental bodies have acknowledged publicly that some form of management of those sites will have to occur into an indefinite future. According to official documents, timelines could range from years to decades to centuries, with no definitive endpoint depending on what mitigation strategies are used. There was a very technical assessment done of the pollution plume that you see depicted there in the kind of pinkish purple on the map on the left-hand side there. That highly technical report was published in 2012. It's many hundreds of pages long. But one of the sort of takeaway conclusions from it was that if the goal was to reach EPA regulated thresholds for TCE in drinking water in 90% of the plume, then anywhere between 500 and 700 years would be required to reach that threshold. So in other words, something like 3 times longer than the United States has even existed. So meanwhile, the technical analyses used to calculate toxicological risk from the TCE plumes to people living and working in the valley introduced their own set of indeterminacies. And this is shown on the right-hand side of the slide, where just an excerpt showing the actual quantitative formulas that were used to determine these toxicological risks. The EPA decided that cancer would be the sort of metric to be used, and then crafted a formula for determining risk. So despite being highly quantitative, the EPA's risk calculations introduced indeterminacy by smuggling in a highly specific personhood under the guise of a universal human, thus committing the error of mistaking that specificity for a universal category of human harm. What do I mean by that? Well, when you sort of dig into those formulas that you see on the right-hand side of the screen, what you start to realize is that the formula used to calculate risk to human health made certain quantitative assumptions. For example, a body of 70 kilograms that drinks 2 liters of water a day and which is exposed to TCE either in the workplace or in the home, but not both. These assumptions, there are others, enact the human of human harm in highly consequential ways. There are obvious and substantial numbers of people who live and work in the plume zone who do not fit those assumptions. Children, for example, typically do not weigh 70 kilograms. People who work in facilities affected by TCE contamination and who live in homes subject to vapor intrusion from the TCE plume in the groundwater. Because the quantitative calculations that you see on the screen there do not account for these cumulative or combinatory factors, anyone who doesn't match those assumptions can never be sure about their probabilities of harm from TCE contamination. In this real sense, anyone not matching the categories of the calculations lives in and with toxic indeterminacy. Now, this kind of situation, of course, is not unique to Silicon Valley or even to the electronics sector. However, The electronic sector, since its earliest days in the Valley, has been presented by its proponents as a clean industry, unlike the dirty smokestacks of the past. I would argue even, more broadly, there's a kind of ongoing mythologizing of the digital as ethereal, that is immaterial, that kind of carries on this tradition of storytelling. Okay, so let me try to bring things together in the last few moments by helping us think through how scale, magnitude, and indeterminacy matter for acting on the bin. So this is a number for household collection of post-consumer electronic waste in the EU. These are the EU's own published statistics, 3,862 kilotons. And what is important, as I've been trying to argue throughout this talk and in other bits and pieces of my my published work, is that it's very important to think about these numbers and their apparent size in the proper relations with which they sit. And in my view, that is in relation to all phases of the lives of electronics, or what bring electronics into existence, which would have to include everything from mining, which you see on the left-hand side of the screen, to manufacturing, that little factory icon. You could include transboundary shipments of discarded electronics, such as that covered by the Basel Convention, that little globe, as well as post-consumer recycling. And I just want to point out a couple of important things here. So one, if you look at the left-hand side of the screen and the number for mining, that is waste arising annually at a single copper mine in Chile. This is the Chuquicamata mine. These are published numbers. The electronic sector is the second largest consumer of copper worldwide. So I would just point out that if we could find some way to reduce the waste arising just at the Chuquicamata mine by 1%, we would have found something equivalent to reducing the EU's post-consumer e-waste collection by 28%, which you see over on the right-hand side of the screen. So there's a couple of things there to point out, and among them are that when we're doing our research on waste, dirt, discards, it is crucial to be thinking about the solutions, if we're offering them, where the action we claim they are taking and modifying, and whether they then reach beyond the post-consumer realm back up the stream. And if they, and then I should say, secondly, what are the most important areas or parts of the overall lives of the kinds of things that we all pay attention to? What are the largest magnitudes where pollution and waste is arising? Are our proposed solutions and concerns directed to for lack of a better term, the right parts of the system? So I end on a somewhat, I suppose, open set of questions that I hope might be a kickoff for questions and discussion. And for the moment, I am just thankful for your attention and for the opportunity to be with you in the room today, virtually or otherwise. Thank you so much.